SwayamPrabha. Digital India. Educated India.
Hello and welcome to this lecture number 6 of the course Robot Motion Planning. In the last couple of classes, we have looked at the basic background review of mobile robots and serial arms, that is forward kinematics, inverse kinematics, transformations, to give you an idea of how robots move and how do we analyze robotic systems. Okay. Now, using that knowledge, we'll move on from today to the formal study of the course Robot Motion Planning. So today we'll start off with the first and the earliest algorithms, which were called the bug algorithms. Now, as the name suggests, bug algorithms means the way bugs move around. Bugs means like ladybird, cockroach. You must have seen them moving around. So that is where the idea of bug algorithms came from, and these are the earliest algorithms. Okay, so we start the study of our formal course today after the revision. Today also I'll quickly review what we had done in the last couple of classes regarding forward kinematics, inverse kinematics, and then we'll move on to the earliest bug algorithms. Now, as the name indicates, bug algorithm, you can already see a bug on the screen, and it is showing that this is a ladybug and how the bug is moving from one point to another point. It has legs and it is moving forward in a straight line. Now, if there is an obstacle, the bug will avoid the obstacle and it will simply go to the other side, avoiding the obstacle, right? So, the earliest bug algorithms were designed after looking at the way insects move in nature. Now, before we move on, let me very quickly go into forward and inverse kinematics. So in the last class, we looked at forward and inverse kinematics, and we said that if you have a two-link manipulator system like this, okay, this is two links for simplicity. This is my x-axis, y-axis, and this is my point xy. So in terms of the link lengths L1, L2, and the link variables theta 1 and theta 2, I can write this as x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay. Now, in forward kinematics, I'm writing it in short by Fk, where we are given theta 1, theta 2, okay, say numerical value, some numerical value, and we are asked to find what is xy. Okay, this is my forward kinematics problem. Now, it's very simple because in these two equations, equation 1 and equation 2, we can simply put the values of cos theta here, cos theta 1 and theta 2, and we can get what is the values of x and y, right? So, this is very, very simple. Whereas in inverse kinematics, that is IK, what we are given is given xy of the end effector, find theta 1 and theta 2. Okay, this is a little bit more involved. Why? Because you can see that the way this terms appear, it is cos theta 1 plus theta 2, so we cannot directly solve. Okay, and also there is the question of multiple solutions. Okay, so there are multiple solutions which are possible. So in the last class, we looked at the inverse kinematic solution of this two-link arm, and we found theta 1 and theta 2. So squaring and adding, so squaring and adding equation 1 and 2, we basically got cos theta 2, where theta 2 was equal to, so cos 2 was equal to x squared plus y squared minus L1 squared minus L2 squared divided by twice L1 L2. Okay, and from cos theta 2 we got sin theta 2, which is root 1 minus cos 2 squared, and then we use the atan function to get theta 2 was equal to atan sin 2 and cos 2. This gave us the positive solution. Okay, and once you get the positive solution, what is the other solution? So it will become minus theta 2 is one solution, the other solution, and then you have to find what is theta 1 dashed. Okay, and that we found geometrically by using geometry, and you can also find it by using algebraic method, but this is an easier method. Geometrical methods are easier. So this is my xy and this is my L1 L2. So we have got theta 2, that means I have got this angle theta 2, and what I want to find is theta 1 now. So geometrically we defined, we completed this triangle. So this triangle here like this and this triangle here. So what we did is, what we did here is we defined an angle called alpha and we defined another small angle called beta. Okay. So what we found is that theta 1 is equal to alpha minus beta as shown in this figure, right? And then we found expressions for tan alpha. So tan alpha is equal to y by x, and tan beta is equal to L2 sine 2 divided by L1 plus L2 cos 2. Okay. And then we use the formula tan alpha minus beta is equal to tan alpha minus tan beta divided by tan alpha plus tan beta. Okay. So this is what we did in the last class, and from here you can find, taking tan inverse, you can find what is theta 1. So once you find theta 2 and you find theta 1, then the problem is solved. Okay. Now we will be dealing only with two link systems here in our course, because it is simple. If you go higher than two links, it becomes more complicated, the kinematics. So this is just to understand the forward kinematics and inverse kinematics of this two-link manipulator system. Okay. So what is the problem here? What is the problem statement? The problem statement in motion planning would be that if you have an obstacle here like this, let's say this is an obstacle, green color obstacle, and you want to go from this point to this point. Okay. So this is my goal and that is my initial point. How many ways are there? And if there are large number of ways of going from this initial point to the goal point, then which path is going to give you the least energy path? Okay, least energy or least time or least distance, whichever way. Okay, so this is basically the path planning problem, where you are given an obstacle and you have a robotic mechanism, either a serial link or a mobile robot, and we are asked to find what is the shortest path. Okay. Now, so in order to find the energy, we looked at the concept of Jacobian and singularity. Okay, and we said that for this manipulator system, I'll draw it very quickly here. For this very manipulator system that I just drew, x is equal to L1 cos theta 1 plus L2 cos theta 1 2, and y is equal to L1 sin 1 plus L2 sin 1 2. Right. This is the same figure that I drew some time back. L1, L2. This is theta 1. That's theta 2. Now, if I take the derivative of this, basically I want to find the relationship between the velocity at end effector and joint velocity. Okay, so I want to find the relationship between the end effector velocity and the joint velocity. Why? Because as far as the control system is considered, we are going to control the velocity of the end effector by controlling the joint velocity, because at there is a motor or an actuator at the joint which we are controlling using the control system, right? So we are more interested in looking at the velocity relationships, plus we are interested in the energy consumed. Now you know that more the velocity, more will be the energy. So this velocity and energy are related. Okay, that is also the reason why we need to look at the relationship of the velocities. So in these two equations, we see that x and y is a function of theta 1 and theta 2. So it means that I need to find the derivative of this partial derivative with respect to theta 1, then with respect to theta 2. Okay, so if I do that, I get dx is equal to minus L1 sin 1 minus L2 sin 1 2 minus L2 sin 1 2, and dy is equal to L1 cos 1 plus L2 cos 1 2 plus L2 cos 1 2, and if I write in matrix form, this is d theta 1 d theta 2. Okay. Now this is called the Jacobian, and in this particular case it is a 2 by 2 matrix, and we can write it in short at x dot is equal to j into theta dot. Okay, where what is x dot? X dot is the end effector velocity, and this one is the joint velocity. Okay, now it is you would understand that this mapping is not 1:1 mapping. What I mean by that, suppose I give I want end effector velocity of 1 meter per second. It doesn't mean that I will need a joint velocity of 1 radian per second. It's not 1:1. Okay, so what we are looking at is, if I draw it this way, so this is my joint velocity, velocity, and this is my end effector velocity. There is some mapping which goes on. Okay, so we are interested in looking at this mapping, and this mapping is controlled by the Jacobian. Okay, so things like whether it is linear, whether it is non-linear, whether the mapping exists at all. For example, in a singularity, the mapping may not be there at all. Okay, so what we are interested in is trying to find the minimum energy. Okay, and we saw that x dot is equal to j into theta dot, and what we are interested in is theta dot is equal to j inverse of x dot. Why? Because we are interested in controlling the velocity of the joint. That's how we control the robot, right? So what we see is theta dot is equal to adjoint of j by determinant of j, okay, into x dot. Okay, now this relationship shows us that if determinant of j is equal to 0, then theta dot is equal to infinity. Okay, so as the determinant of j is going towards infinity, going towards 0, implies that theta dot is going towards infinity. Now going towards infinity means infinite energy, which is obviously not possible. Okay, so these points are called singularities. So it serves two purposes. Number one is if you want to find the minimum energy requirement. So minimum energy would mean maximize determinant of j directly, right? So that gives us one way. The other is minimum energy means stay far away from singularity. So the nearer you come to a singularity, the more you'll have your energy requirement will go up. Okay, and finally it will go to energy. It will go to infinity. Okay, so it serves these two answers of minimum energy. That first you have to maximize determinant, and then you can minimize the energy also by staying away from singularity. So, for example, I'm just giving an example. If there is a singularity, let me take the example of this two-link manipulator. Okay, so these are small, and so the work volume of this will be something like this. Okay, this will fold this much and here. So this is a boundary singularity. This is also a boundary singularity. So if you are trying to go in a path like this, which is coming very near the singularity, okay, that will consume more energy. Whereas if you take a path which is going far from the singularity, away from the singularity somewhere here, then that is going to take minimum energy. It will take lesser energy. We also found for a two-link manipulator, we also saw that minimum energy corresponds to theta 2 equal to 90 degrees and 270 degrees. Okay, so if you when you're planning the motion, we can make use of this business of minimum energy to find a path for which the energy consumption is going to be minimum. Okay, so now let's proceed with this background, what we had done in the last class. Now, as I said in the last class, please, I'm doing it in very brief. If you're interested in looking at more details of this, please refer to the Introduction to Robotics course in NPTEL, or look at the textbook where they discuss kinematics and forward kinematics, inverse kinematics, then manipulation ability, determinant of j in more detail. Okay, here we are doing just how much we need. Okay, so we are going to study about serial arm robots, and it will be limited mainly to 2 degree of freedom system, at most 3. Now, the other kind of robots that we are going to look at are mobile robots. Okay, so mobile robots can be of differential drive type. Now, a differential drive robot is as shown here in figure A, where this is a robot which has 2 wheels and there is no connection in the wheels here. So, for example, this connection is not there. Okay, and each of the wheels is driven by a motor. So, motor here and motor here, they are independently driven. Okay, now we have a frame. This is my frame. This is the fixed frame, or the reference frame. This is my x, that's my y. Okay, now it is making this. What we do is, from the center point of the 2 wheels, we have an x-axis. So let's call it the axis of the car, the axis of the mobile robot, and this is making an angle of theta with the x-axis. This is my x. Okay, so what we see here is that we can control this robot by looking at omega 1, omega 2. Okay, by controlling omega 1 and omega 2, we basically control the position of this one, that is my x and y. Okay, so x, y, and theta I need to control, right? So in order to control this, basically I have to control. I can so my control input is my omega 1, omega 2. I have no other control input. So with 2 control inputs, I'm controlling 3 outputs now, x, y, and theta. Okay, so this is one type. So let's call it type. Let's call it type 1. This is type B. The same thing. I'm going to put a reference frame here. This is my x and that's my y. Now, in this particular case, this is a differential drive. but what you can see is that the wheels at the rear wheels are joined and they are driven by a drive. It can be a motor, it can be an engine. So it has an angular velocity omega, and there is a steering angle in front. So this wheel in front can be steered. So it is something like this is the auto rickshaws that are that you see on the roads. Okay, so they have a back wheel drive, and then there is a steering in the front. Okay, so in this case also we have to fix our axis. Okay, so this is my x-axis and that's my y-axis, and this is the coordinates x and y of the center of that point. Let's call it P. And again we have theta is the angle which you are making with the x-axis. So x, y, and theta, okay, are the outputs, and the input is what? There is a drive and there is a steering. Okay, so let's call this omega and theta dot. Okay, so we have a drive and a steering, and both of this is controlling these three output x, y, and theta. But the structure of the vehicle is different. You can see that the rear wheels are, both of them are driven, and then there is a steering in front. Now in a car which is four-wheeled, which you can see here again, this is a car. So the rear wheels are driven with a velocity omega, and there is a steering in front. Okay, so this is the steering of the wheels. So this one has a steering angle here. That's my phi. Okay, so how do we control the car? We can control the speed of the car by changing omega, and we can control the direction by changing phi. And again, at this point we have x and y, and then we have phi, which is the steering angle. So my input is omega and phi, and my output is x, y, and theta. Okay, so these are the different types of mobile robots that we look at as we proceed. Now, so let us proceed from here. Now, the earliest bug algorithms, the idea for them were obtained from basically looking at insects, like a motion of bugs and insects. Now, what is a bug? Bug is an insect. You know, there are different kinds of bugs. There are beetles. Okay, so there are beetles which look like this. I'm sure you must have seen them. Okay, they have wings also, some of them like this. Then there's a ladybird as shown here. Okay, then there is a cockroach, the good old cockroach where you can see in your houses or in other places. Okay, where the cockroach has 6 legs. This bug also shown here has 6 legs. Now, if you observe this, I'm sure you must have observed that the insect is going straight. Now, suppose there is an obstacle here. Okay, suppose there is an obstacle here. Okay, what it will do is basically, after it hits the obstacle, okay, or even before it hits the obstacle, it will try and bypass the obstacle like this and go from the other side. So either it will go on the right side or it will go on the left side, right? Now that is one. So what we are seeing is that it has legs for motion. That's how it is moving. Okay, it has some sensors for sensing obstacles. Okay, obstacles, food. It has sensors for that. Okay. Now, in the case of the ladybird that we are seeing that is moving here, it has 6 legs and it can walk, turn. In the case of the cockroach, it also has 6 legs and it has these feelers. Okay, these feelers are the sensors where it can touch something. For example, if there is an obstacle here, let me draw it like this. So if there's an obstacle here, okay, it can touch that and it can feel that, okay, something is there. Okay, so this is basically the legs are for motion and the feelers are for sensing. So what we are seeing that if you are going to design a mobile robot which can actually move around like an insect, okay, it must have some kind of motion capability. So either it has legs or it has wheels. Okay, insects don't have wheels, they all have legs, but mobile robots have wheels. Okay, and there must be some kind of sensor for sensing the environment. And if there is an obstacle, it must sense, and then there must be some kind of a plan, okay, plan or behavior, okay, of what is the objective here. So, for example, if this ladybird wanted to go from here to here, like that, so it can bypass that and go there. Okay. Now, if the cockroach is trying to avoid this obstacle, it will touch the obstacle, and it understands that the moment it has touched, and then it can change its path, okay, either that side or this side. So, what is the behavior? The behavior is the change in path. Okay. Now, in order to do that, in order to have a particular behavior and to have a particular kind of plan, then it needs, number one is some ways of moving, legs or wheels, and it needs sensors also to sense the environment, right? And then it can enforce a plan. In this case, the plan is very easy for the cockroach. Go left, go right. Okay, go left or go right. It can't do both. Okay. Similarly, for the ladybug also, it can go left or it can go right. So we are in this path planning and motion planning course. We are interested in finding the path in going from an initial point to a goal point, maybe avoiding obstacles. Okay. So here the mobile robot will need some ways of moving forward, and it will need some kind of sensor for sensing the environment. And then it will have some kind of a plan as to when it hits the obstacle, what to do. That is the behavior. Okay. In this case, it is very simple: go left or go right. Okay. So the earliest ideas of bug algorithms came from this motion of bugs and insects. Now let's come to mobile robots, which we'll be dealing with. So working with mobile robots having differential drives. Now this is a differential drive mobile robot. So you see that there are two wheels and there are motors there, and these motors are independently actuating the two wheels. Okay, and there is a caster wheel in front. So there is a caster wheel in front which is providing support. So this is similar to our figure which we showed some time back, that there are two wheels and there is a caster wheel here. So this is omega 1, omega 2, and it basically moves by controlling omega 1 and omega 2. In front there is an ultrasonic sensor. Okay, now this ultrasonic sensor basically can check for depth or distance. So if there is something in front, it can sense that there is something in front and it can enforce some kind of a behavior. For example, go left, go right. Okay, or if there is something in front, just stop. Now this is controlled by in this particular case by a Arduino microcontroller. So the behavior of this will be a program, okay, which will be written in the form of a program, and the behavior is going to be embedded in a program. Okay, so these are the elements is a program. So the program is the one that is going to actually determine what the robot is going to do. So the program is the one that will find the path. So in path planning, our essential function is to write a program or an algorithm that will enforce some kind of a behavior or a plan. Okay. So you might have been familiar with this kind of robots, which a lot of students make in high school these days, and they are available in supermarkets. So we can do motion planning, path planning with these type of very, very simple robots. Now this shows the internal details of the mobile robot. So it has DC motors which are driving it, and in the previous one there was an ultrasonic sensor which is sensing if there is an obstacle in front. In this one there is an IR sensor there. So IR stands for infrared sensors. So this also can check, it can check for color. So for example, this is using if you're following a line, for line following kind of robots. Okay, so if you draw a line like this, say for example I have a black line and I leave the robot on this black line, so what it can do, this infrared sensors can sense, okay, where is the black line. Say for example, these are 3 infrared sensors. Okay, so you can have a logic to ensure that the center infrared sensor will always remain on the line. So the moment 2 of this comes out, it immediately understands that it has gone left, so it has to actuate the wheels to go right. So that's the behavior of the robot now. Okay, so this is just to give you an idea of what the path plan actually does, or what is our objective here. So there are different kind of sensors, there are actuators for the robot, and we can enforce different kind of behavior of the robot. Now very quickly looking at the ultrasonic sensor. So ultrasonic sensor basically works on the has a ceramic transducer inside here, which is basically a piezo. So piezo crystal, as you know, that if you give pressure it will produce charge, and if you give it charge it will produce it is going to expand. Okay, so it will expand here. So what is done is that this piezo crystal is actuated at a particular frequency. Now this is shown here. So the piezo crystal is being actuated at a particular frequency and it is vibrating at the, so this piezo crystal crystal is getting actuated at a particular frequency, and this is the ultrasonic frequency. Okay, so because it is vibrating at that frequency, it is going to give out an ultrasonic wave. So the ultrasonic wave goes out from the front like this. Okay, so this is an ultrasonic wave. Now, the moment there is something in front, it will hit that object and then it will come back. Now, once it comes back, it causes a pressure on the crystal, and that pressure produces a charge. So, depending on how much time it took to go and come back, you can compute, you know, the velocity of sound in air, so you know exactly how much time, what is the distance of the object from the sensor. So, this is the out signal, this is the in signal, so this is my in signal. So, the distance from here to here is my del t, the time that it took to go and come back. So, now you know what is the distance of the object. So, these are ultrasonic sensors which are very simple, and they are extensively used in mobile robots to check if there is some object in front to avoid obstacles. Infrared sensors, again, they can also sense reflective surfaces. Okay. Now, in an infrared sensor, there is an emitter. You can see there is an LED there which is emitting light, and there is a photodiode which is a receiver. So, this LED gives off light, and the reflective surface reflects this light, IR, infrared rays, and it comes back and gets received here. So, exactly here also, it can exactly figure out color of an object or reflective surface in front. Okay. So, IR sensors can also be used in mobile robots extensively. Now, you can see ultrasonic sensors and IR are non-contact type. They don't touch. Okay, from far they can make out. So, the robot can enforce a behavior simply when it gets the signal input. So, if the program receives the signal that there is something in front, so it can immediately change its behavior. Okay, it can try and avoid the obstacle. The other kind of sensors are the sensors which are contact sensors, like the one that you looked at with the cockroach. Okay, so we looked at. So in the case of the cockroach, we saw that so there is a stylus in front. So this stylus is there. The stylus is there for touching. Okay, it is very, very sensitive. It can sense not only obstacles, it can sense if there is food, if there is chemicals, it can sense. It's like our tongue basically. And with this, it can sense if there is an object in front and then enforce its behavior. So in this particular case, it has to physically touch the object in this robot, where you can see that this is a stylus. Okay, so it's a stylus, and if there is an object it is touching, what will happen is the stylus will bend. Okay, so if it was not touching, it would be straight like this. Now, because it is touching, what is happening is that it is getting bent and there is an angle there. So, if there is a sensor here, we can use a potentiometer or an encoder, which will actually sense that the stylus is touching something. Why? Because it has bent. So, basically, you're looking at that angle alpha. This angle theta. Okay. So, basically, if it was not touching, it will be straight. Okay. And if it is touching something, it will immediately bend. So, if it is touching something, it will become like that. It's touching. So, basically, this is being sensed. Okay. And based on that, we know that there is something in front. This is also a very simple sensor for a robot to make, and robots use this kind of sensors for touch the wall and follow the wall, follow the object, etc. The other is a tactile sensor, which is actually sensing the pressure. Okay, so there are different kinds of touch sensors or tactile sensors. So this one is a capacitive array. So if this touches something, immediately what happens is there is a plus minus on top. So it is a grating like on this side there are gratings like this. The bottom side there are gratings like this. So if it touches, what will happen is, let me explain it like this. If it touches, what will happen? There is a plus and a minus. So there is one on top and there is one at the bottom. So it's something like this. Okay, and there is a plus on top. So this is plus, that's minus. So if you press it, what will happen? This will get shorted. The moment it gets shorted, it is something like a key on keyboard. As soon as this is pressed, that part is shorted and it gets a signal. So the robot understands there is something in front. This is another kind, pressure sensor, where if you touch, this is a resistive pressure sensor, so there is a change in resistance. So it immediately understands that it has touched. Okay, this is something like our strain gauge. So these are contact type. The earlier ones we have seen are non-contact type, IR and ultrasonic sensor. Now, depending on the kind of sensor we have, the kind of range of the sensor, okay, we will have to enforce different kind of plans. Now, let's move on further and now come here to the bug algorithm. Now, what is the object of the bug algorithm? What is the objective of the bug algorithm? The objective is to find a path. So, objective, find a path from initial point to goal point. Okay. So this is shown in the figure here. So I'm marking my x-axis and my y-axis, and this is my start point. This is start. Okay, we call it start, and that's my goal, and these are obstacles. Now a couple of simplifications we make, or assumptions we make. The first is that the robot is a point robot. It has no physical dimension. Okay, so we are considering this robot to be a point robot. Next is it has a touch sensor to detect the contact with the obstacle. So the moment it makes contact with any obstacle, it knows that contact has been made. Okay. Now what is the objective? The objective is to find a path from the start point to the goal point. Okay, avoiding the obstacles. Okay. Well, not avoiding the obstacle, it is touching the obstacle, not going through the obstacles. Okay. So the objective is to find a path from the initial point to goal point. Okay. What is the plan that we're going to enforce? Okay. The plan that, or the behavior that we're going to enforce, is that it will have a motion to goal behavior, and it has a boundary following behavior. Okay. Now what is the start of the algorithm? Now something to note here is that if I asked you which is the path, you can simply tell me that go like this, or rather don't go like that, go like this, go like this, go like this, go like this. Okay. Now we have eyes, so you can see there's an obstacle there and the goal is there. The poor robot doesn't have eyes and it's in 2D, flat ground. Okay. So for us it is very easy to say where is the path. For a robot, for a program to find out, it's not that easy. Okay. So the program has to be written such that it can take the robot from the start point to the goal point. Okay, and it cannot go through the obstacle, of course. The assumptions we have made: the robot is a point robot. It has a touch sensor to detect contact with obstacles, so that it doesn't try and go. It cannot go through the obstacle. And the input to the algorithm or the program is the start point, goal point, and obstacles. Okay, so we have to write a program which will take the robot from the start point to the goal point. Okay, and not through the obstacle. It cannot go through the obstacle. Okay. Now, what is the behavior that we're going to enforce, or the program is going to enforce, or the plan that is going to be enforced? Now, the first thing we can see is that the robot should move towards the goal, right? Always. So, if the robot starts going this side, then it's going away from the goal. It's not solving anything. Okay. So, the first thing is motion to goal behavior. So, the robot should have a motion towards the goal behavior. Okay. The second is it should be boundary following, or rather obstacle boundary following, because it cannot go through the obstacle, it cannot do that. So it should be able to follow the boundary or the contour of the obstacle. Okay, that is the essential plan for the bug algorithm. So what are we given? We are given start point, end point, goal point, and the obstacle. Now the program has to enforce number one, motion to goal, and boundary following. Let's see how that is done. So here we have, so in the first algorithm, we have to reach a goal point from a start point, avoiding the obstacles, right? So this is the problem that we are looking at here now. Okay. Now the robot is a point robot and it has a touch sensor. Okay. So now we are supposed to write a program which will actually perform or execute this motion now. The first algorithm that we'll look at is the bug algorithm or the bug one algorithm. So there are different ways by which you can solve this problem. Okay, let's see how we can think of solving this problem logically. Okay, so we have one here and we have another one there. Okay, obstacles. So these are obstacles. 1, obstacle 2. Okay, let's call this my goal point. This is my start point. That's my start point. Okay. Now the first thing is that it should have goal following behavior. This is something we have seen. So number one is that goal seeking behavior. That means it should always try to go towards the goal, because I want to go towards the goal, right? It shouldn't go in some other direction. So the first thing that we can do is we can connect the goal with a straight line. Okay, so we connect the goal with a straight line like this. Okay, now if there were no obstacles, it will probably follow the straight line and go there. Now because there are obstacles, what it does is it follows this straight line until it comes to the hit point. Okay, so we call this Q1H. Q1H is the hit point on obstacle. So Q is the hit, Q1H is the first hit point of the obstacle. Okay, so we're writing a program where the robot is going towards the goal. You know the direction of the goal, which has been given. Now, as it is going, as we connected with the start point and the goal point with a straight line, we follow the straight line. The moment it hits an obstacle, we know that it has hit. It has touch sensor, so it knows it has hit. Now what it does is it circumnavigates the obstacle. Okay, so basically it goes around like this, all around the obstacle. So it explores the obstacle and comes back here. Okay, so it explores the obstacle and then comes back there. Okay, now once it has explored the obstacle, now it knows that this is the shape of the obstacle. Okay, the mobile robot has actually found out. Now what it does next is it follows the, I'll just change the color here. So this is next. What it does is it knows this is by Q1H now, and it identifies the Q1L now, the Q1 leaf point. So the Q1 leaf is the next point, which is here. I'll just draw it again. So it did that, came back here. So now it identifies the Q1 leaf point, which is here. So my initial straight line point was like this. Okay, so now what it does is it identifies the Q1 leaf. Q1L stands the leaf point on this circumference of the obstacle. Okay, now that Q1 leaf point is the nearest to the goal or the next obstacle. So whichever point is nearest to the goal, or it is nearest to the next obstacle, that is the Q1L point. And from the new Q1L point, again it will continue. So how it will continue? The same thing it will do like this and then go here. Okay, the moment it has gone there, what it will do? It will circumnavigate once like this and come back here. Now it has seen the full obstacle. Now after it has seen the full obstacle, what it will do is, this is my Q2 hit point. Then it will identify the point which is nearest to the goal. This is the point which is, so this is QL2, the Q2 leaf point. Okay, so this is the Q2L point. Okay, so now it has come here and now it goes here. So what it is doing is it is going like this. It is circumnavigating once, coming back to this point. Then it is finding the leaf point which is nearest to the next obstacle or to the goal. Okay, and then it is finding the path which is nearest to the next obstacle. It is circumnavigating again, full round like this, coming here, finding the point, the leaf point, and then it is going there and getting the goal. This is having goal seeking behavior, that is one. Number two is it can circumnavigate the obstacle. Okay, so goal point and circum. Now, as I said before, this is a point. Robot is a point and it has no eyes, so it can't see. It is simply, it's a program which is going to execute this motion. It will always go towards the goal, and if it hits an obstacle, circumnavigate, find the leaf point which is nearest to the next obstacle or the goal, and then go to the obstacle, circumnavigate, and then go to the goal in this case. Now this search is an exhaustive search and it is not fast. Why? Because it is circumnavigating each time. So if there's a long obstacle, you can imagine it will keep going all around the obstacle, where it actually doesn't have to go do that. So for example, if the goal was somewhere here, okay, so that was my goal, then for nothing it will just be going round and round the obstacle, and then it will come here, then find the leaf point and then go there. So, but this is an exhaustive search, which means that it has looked at all the possibilities. This is the earliest algorithm called the bug algorithm. Now you can write a very simple program which can do that, because a point has coordinates x, y, and when it is touching, you know the circumference of this obstacle, right? So whenever x, y is hitting or touching that circumference, you can find out geometrically. So you know it has touched. Now you know the shape of the object, so you can circumnavigate very easily. You can find the Q1L point, then go to the next obstacle. So this has to be done geometrically. Okay, so path planning is a geometrical problem. Okay, so what does the algorithm look like? So start with QL0, which is the start point. Okay, and then the first thing is from QL1 move towards to the goal point. Okay, until goal is reached or obstacle encountered at Q1 hit. So this is what we did. So you start off from the start point, go towards the obstacle. If you hit an object, okay, that is your hit point Q1H. Okay, follow the obstacle boundary by moving left or right. Now please note here that it is left or right. You can't do both. Okay, you cannot go left and right at the same time. And then until Q goal is reached or Q1H is re-encountered. Determine the point QLL, leaf point on the perimeter, that is the shortest distance to the goal. Go to QL1 and then move forward. If you reach the goal, then exit. Okay, exit with, if move towards Q goal moves into obstacles, then exit with failure. Okay, so this basically means that we are going to go to this obstacle, circumnavigate, find the leaf point, go to the next, and then proceed that way. Okay, failure cases of this, will it always work? Well, if there are objects which are enclosed objects like this, okay, this we can understand very easily, that if you have an obstacle like this, and you can see that you have a start point here, and you have a goal point there. So what will happen is the algorithm will function, right? Because it cannot see that the obstacle is enclosed. So it will first make a straight line, then follow the straight line, get a hit point. So this is Q1 hit. Circumnavigate like this, come back here. Okay, try to find the nearest point to the obstacle, and it cannot do that. So this will end in failure. Okay, so in this, the algorithm will start by going towards the goal. It will hit the boundary. It will circumnavigate, come back here, try and find a point, a leaf point, but the Q1L does not exist. Okay, because it cannot go out. There is to the outer boundary. There is no connection, and there is no way it can go to the goal. So this will be a failure case. Okay, so it should be able to say that there is no path. Next is so when you look at this, whenever we look at path planning algorithms like this, okay, the thing that comes to your mind is there a better way of doing this? Okay, is there a faster way? So the faster way of doing this is the next one, which is called bug 2. Now in bug 2, what we have seen in the previous case is there is no need to really go round the obstacle all the time. So for example, if I had an obstacle like this, and the goal was here, and the start was here, then what it would do is it will come here, then go around like that, and then go here, and then go here, and then go there. That's a bad way of doing things. Okay, well, it's not a bad way of doing things, but that is one way of doing things. But the other way could be that you connect this with a straight line and follow the straight line. If you hit the obstacle, go down the obstacle, wherever you are getting the straight line, you follow the straight line and then go to the goal. So I put a straight line like this. So from here I go here, hit, I go like this, hit the straight line again, and then I go there. I don't circumnavigate. Okay, so this is showing the path, which is the bug algorithm 2. So what we do here is we connect the goal and the start point with the M line, and follow the M line. So you can see that it is following the M line like this. So it has gone. The moment it hits, so Q1H, it will go left like this until it finds the line again. Once it finds the line again, this one becomes Q1 leave. It goes there, it becomes Q2 hit. Okay, and from Q2 hit, it circumnavigates, it goes on the left side like this and gets that and goes there. Okay, this was much faster because it did not circumnavigate. Okay, so this is bug 2 algorithm where we follow a line which is called the M line. The moment you hit the obstacle, you circumnavigate until you hit the line. The moment you get the line, you follow the line. Don't follow the obstacle. Okay, and then go to the obstacle. Once you hit the obstacle again, then go to the find the line again, and then go to the goal point. Okay. Now this is faster. Now you can see in this particular case also, from the start point to the goal point, connect with a straight line, follow the straight line, come like this, follow the obstacle boundary, come like this, hit the point and go to the goal. Okay. Now this is the bug algorithm 2, the program, okay, the logic. So in all the, when you're writing a program, okay, there is a plan, okay, and there is some kind of a logic, let me call it a logical plan. We start with Q1L, okay, so Q1L moves towards the goal along the M line. So we fix an M line first, and then from the first leaf point, which is the start point, so this is my start point, it goes to the goal point following the M line. The moment it hits an obstacle, okay, if goal is reached, exit. Now if goal is not reached, then follow the boundary, move left or right. Okay, left or right. You have to choose one, you can't do both. So go left or right until you hit the M line again. The moment you hit the M line, follow the M line again until you reach the goal or you reach the boundary, and then follow the boundary again, hit the M line, and then go to the goal point. Okay, this is basically the bug algorithm 1 and bug algorithm 2. Now bug algorithm 1 is an exhaustive search. Okay, it is more complete. It is more complete in the sense that it can find all possible paths. In that sense, it is more complete. Okay, so if there is more than one path, it can find multiple paths. Now, bug 2 is what we call a greedy search algorithm, in the sense that it is an opportunistic search. Okay, and it's a greedy search because it tries to find the solution faster. Okay, and it is faster, as you saw in the previous case. So the question comes, which is better, bug 1 or bug 2? Now in path planning, you'll always see that this question comes up. Is there a better algorithm? Is this better than that? Okay. Now it would depend on the situation, or case to case, it depends. Okay. So it would just appear to us that bug 2 is better, but you'll find that that is not so. It depends on the situation now. So let's look at this now. So in this particular case, comparison of bug 1 and bug 2, the obstacle shape in which bug 2 does better than bug 1. In this particular case, as shown on the left. Okay. So what we are given is the goal here, and we are given a start here. So it goes straight, gets the M line. So let me draw the M line. It follows the M line, hits the obstacle, circumnavigates, hits the M line again, then goes like this, and then goes to the goal. So this is faster. Okay. Whereas if I was doing this with the bug 1 algorithm, then what it will do is bug 1 will go here, then it will go circumnavigate like this. Okay. Then it will go back here, it will go there, then it will circumnavigate everything here, then go here, then go there. Okay. So bug 1 is the green line, and bug 2 is the blue line. So we can see in this particular case that bug 2 is faster. Okay. What about here? Now in this kind of a situation, we want to go from here to here. There, that's my straight line. Okay. Let me follow the straight line and see what happens. Okay. So I'm following the straight line, and let us see what happens here. So I go straight like this. I hit the obstacle. Now I go like this. I go like this. I go like this. I go like this. Like this. Like this. I hit the obstacle. Okay. Now I can come back like this, and come back here again. That is one option. Okay. The other is I have my straight line like this. Okay. Remember, you can go left or right only. You can't do both. So here what we do is it follows the line straight, then it goes left like this, it goes here, here, here. It hits the line again, comes like this, come like this, come like this, like this, like this, and is back here again. So it appears that it got trapped in some way. So in this particular case, bug 1 will beat bug 2. So if you look at bug 1, what will happen in bug 1 is it is going to circumnavigate all of this, and then find the path from here, and then find the shortest path. Okay. So in case of bug 1, what it is going to do is it will go from here, it gets that, then it starts circumnavigating like this. Okay, because it is finding the full shape of the obstacle. Then it's coming like this, circumnavigating. Now it exactly knows which is the point where it is the leaf point which is closest to the obstacle. So it will come here and then go there. Okay, so in this particular case, bug 1 will beat bug 2. So you can see that this path planning problem is very much specific to the problem that is being, or the shape of the obstacles, because this is geometry. So it is very much related to the geometry of the problem. Again, this is another case of comparison of bug 1 and bug 2. Okay. So in this particular case, we have a start point. We have a start point and we have a goal point which is inside. So this is my goal point. Okay. So this is bug 1 and that's bug 2. Okay. Now we can see that this is my start point. Okay, start here. So bug 1, what will it do? It will first draw the straight line like this. Okay. Then it will start going straight. Then it will circumnavigate like this, like this, like this, and then come back here. Okay. Now it knows, because it has seen the full circumference or the exterior boundary of the spiral. Now it can find the leaf point which is nearest to the goal point, right? So it will go till here, and if this is my goal, okay, then it will go here and then it will reach the goal from there. Okay. So in this particular case, so where was my goal? My goal was yeah. So after it circumnavigates once, what will happen is it will go like this, like this, like this, like this, like this. Come back here. Next, it has to find which point is nearest to the goal. So it finds that this point is nearest to the goal. So it simply goes there. Okay, so it follows this, goes here, and then simply goes to that goal. So next shot, what it will do is it will come like this, 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 and then go to the goal. It knows what is the leaf point. So this is my Q1 hit, and this is my Q1 leave. But let's see in the case of what happens here. So this is my start, and that's my goal here. Okay. Now let's see Buck 2 what it does. It generates a straight line first. Then what it does is it goes like this. Okay, goes from the right side like this, here, 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 here. Okay. Then finds the line, goes this side. Now it comes down like this, and now what happens is it comes back here again. Now Buck 2 has got trapped. You can see that. So in this case also, in the case of a spiral, Buck 2 loses and Buck 1 wins. So you can see that it is very much dependent on the profile. Now the point robot now has an ultrasonic range sensor. Okay. So we are still with the bug algorithm, but the robot in the previous case has a touch sensor. Okay. But in this case, it has an ultrasonic range sensor. So it can sense the distance to object. Okay. So the range sensor has a finite range of detection, and it can sweep 360 degrees. So if this is my sensor, ultrasonic sensor, it can rotate 360 degrees. If this is my 0 degrees, it can rotate like this full 360 degrees, and it can, so these are the rays, ultrasonic rays which are coming out, and it can sense distance. So if there's an obstacle like this, it can sense that there is an obstacle in front. Okay. The range sensor will prevent the robot from colliding with the obstacle. Okay. Now you can see here that there are two variables. One is the position of the robot X. Okay. And the angle at which it was sweeping, which is the sweep angle, okay, at which it was, so we can call it theta. So this is my angle theta. Okay. So what we need to do here is we need to define a range. We need to define a distance function, okay, which consists of the position where the robot is and what is the sweep angle of the ultrasonic sensor. Okay. So we define a distance function to find the shape of the obstacle, because the shape of the obstacle, let me draw the obstacle having some of the shape, is the ultrasonic sensor is okay. So at different distance, it has different distances at different angles. So the robot X is the same X, but at different angles, at different thetas, you can see that the distance that it is getting of the obstacle is different. Why? Because the obstacle has a particular shape. So basically this rho is what is going to give us the distance function. Okay. So for the same X, for a different theta, it will give you a different distance. And the distance function is defined as rho x theta, where x is the coordinate of the robot, and the coordinate of the robot center, and theta is the angle of sweep. Okay, of the sensor. Okay, so this we are seeing that we are using ultrasonic sensor now. Now, depending on the range of the sensor and what is the sweep angle of the sensor, you will get a different distance reading now. Okay, depending on the shape of the object now. So next, let's look at our raw distance function that we are getting. Now, what is the objective here? The objective here is that we need to find out what is the shape of the obstacle. Okay, so we are using this range sensor, which is going to give us the shape of the obstacle now. So this is my x. Let's imagine this is my x, and theta is going to vary from 0 to 360 degrees, one sweep. And this is the shape of the obstacle that we are getting. Now the shape of the obstacle basically is a function of the distance now. Okay, the distance, I mean this ray, the length of the ray, if I say. Okay, So this is what is giving me the shape of the obstacle now. Okay, and that is my rho x theta. Okay, there is obstacles here. These are called W04, O3, O1, O2, O3, O4 are called obstacles, and the moment it hits an obstacle, you'll get some value for that. Okay, that means that it has some distance. Okay, what is the distance from the sensor to that obstacle? That is what is my rho. So rho is the distance from sensor to obstacle. Okay, and if there is no obstacle, then it will become infinity, of course. This will go in towards infinity. That means nothing is there in front. Okay, so basically we are looking at this distance function rho and then trying to decide the shape of the obstacles. Okay, today we looked at trying to find out the use of bug algorithms, which is based on how bugs move in the real world. Okay, and we also saw that the bugs have locomotion and they have some kind of sensor, for example touch sensors, or they can have vision. Okay, correspondingly in the robot we have robot which moves around with wheels, and the robot has some kind of sensors, so it can have touch sensor, or it can have ultrasonic sensors, distance sensors. Now we stopped at the condition where we are using a mobile robot which is having an ultrasonic sensor, and to check the distance it basically looks at how far the object is, and it derives a function, okay, which is or the distance, or what we call the distance function is a function of the sweep angle and the position of the robot. So today we'll stop here. In the next class we'll continue from here and look at how to figure out the shape of the object, and then how to plan your path from where the robot is to the goal point, and we'll see that it depends on the range of the sensor also. So we'll stop here. Thank you.